Hi everybody, my name is María Valentina Garcia. I'm a physics undergraduate student at Universidad de los Andes in Colombia, and I'm going to talk about a work that was recently published in monthly notices of the Royal Astronomical Society in collaboration with Jaime Forero and Xiaodong Li. The work is called The Cosmic Web Through the Lens of Graph Entropy. To begin, we know that one of the main challenges in cosmology is to describe the distribution of matter in a large scale. For this, there are two mainly accepted methods. One is the two-point coordination function, and the other is the representation of the large-scale structure as a graph. We're going to use the latter one. For this, we use the graph entropy from information theory that has this form and uses the probability shown above that involves the number of nodes from the graph that we are going to use. The graph is called the beta skeleton, and to understand better how it works, we have a plot in the left that shows a set of dark matter halos from a simulation arranged as a sphere. We see that for beta equal to 1, we have a fully connected graph, and for beta equal to 5, we have a graph that has lost its connections. So we see that if we increase the parameter beta, the connections of the graph are lost. So how does this affect the entropy? In the right, we see a plot of entropy against beta. We see that it has a characteristic behavior and that the entropy is affected by the beta. We also see in this graph, in this plot, that the entropy allows us to distinguish between random and clustered points. In this slide, we summarize all the analysis that has been done. We show the influence of different effects on the graph entropy. So from A to F, we show the influence on cosmic variance, orbit geometry, redshift space distortions, redshift evolution, cosmological parameters, and number densities. The most important feature in this slide is that the strongest influence is seen in the number densities. To conclude, we saw that the graph entropy analysis allows us to distinguish between random and clustered points, that the strongest influence on graph entropy comes from clustered points with different number densities, and we show some further applications that are measuring the entropy from different parts of the sky to check for isotropy, building graphs from other quantities to quantify its connectivity properties, and tests for the applicability on observational data. Thank you.